Welcome, wonderful students. This is Mr. Visitor once again. And this time we will look at integration by partial fractions. We will look at integration by partial fractions. And if you don't know what integration by partial fractions is, I think this is the time for you to know. Now, what we are going to do in this, we are just going to start up with something very simple. We will start by looking at a summary. And in our summary, we will say the method of partial fractions when f at x divided by g at x is proper. That simply means that the degree of the numerator function is less than the degree of the denominator function. So this is exactly what we will be looking at, and remember that we are trying to integrate in all this. So we are therefore saying, okay, the method of partial fractions, when, remember this is integration, when we integrate and we find that the degree of the numerator is less than the degree of the denominator, and therefore we refer to that as an improper fraction. This is proper. It's a proper fraction. So a fraction is a proper when the degree, the highest exponent of the numerator is less than the highest exponent of the denominator. That's one way of stating that. And therefore we are saying this is a proper partial fraction in terms of integration. Now, we can continue and say, okay, if we let x minus r be a linear vector, we let x minus r be a linear vector of g at x, which is the denominator in this case. So we let x minus r be a linear vector of the denominator g at x, and we suppose that the linear vector of g at x raised to exponent m is the highest. It is the highest power of x minus r. So the exponent m there is the highest power of x minus r that divides g at x. So this is the way in which we will approach these partial fractions. We will look at this integration of partial fractions in a way that we are saying, okay, the first thing that will be done, I think I lack some light. Okay, I think it is now a little bit clear. So we are saying we will let x minus r be a linear vector of the denominator g at x, and we suppose that x minus r, which is a linear vector of the function, is raised to an exponent of m. It is the highest power of x minus r that divides into g. Okay, that's fine. I know for now things are not clear, but as we continue, I think they will. And then once that is said and done, then to this factor, we are going to assign the sum. We will assign the sum of the m partial fractions. Now, what do we mean by that? When we are saying to this x minus r to the exponent of m that divides into this, we are going to assign the sum of m partial fractions. And then what do we mean by that? Right, we mean the following. We will say, okay, since that x minus r to exponent m divides into this, so meaning we are going to say, okay, since I have f at x divided by g at x, I'm going to say, okay, I'm going to use the alphabet a1 to represent the numerator function, and on my denominator I have my linear factor that divides into g at x, and I'm going to say x minus r. This will be an exponent of 1. Remember, to this, then we assign the factor, we assign the sum of the m terms to these partial fractions. To what? To this factor. Right, so I'm going to say x minus r to exponent of 1, which is a what? Which is a linear factor of the denominator. Okay, plus I'm assigning the sum of m factors. So I will have my a2 divided by x minus r squared. What is this? This is the sum of m factors in that increasing order of exponents. 1, 2, 3, and so on. I can have a3 x minus r to the exponent of 3, and I can keep on doing this till to am divided by x minus r exponent of m. And then we are doing this for each distinct linear factor of g. So for each distinct linear factor of g at x, we are doing exactly that. What are we doing? We are saying, since that we said in summary the method of partial fractions, when we have this, remember we are integrating this. We are saying to you, okay, this is proper when the degree of the numerator is less than the degree of the denominator. And as I'm trying to assign that here, we can argue and say this is true that the degree of the denominator is greater than the degree of the numerator. We are assigning the alphabets A1, A2, and A3 to denote that what we are doing here, it's just us trying to do what now? To this factor, to this factor of x minus r, which is a linear factor of g at x. What are we doing? We are assigning the sum of the m partial fractions. The sum of the m partial fractions in that order of increasing. And therefore, because this is the method of partial fractions, f at x divided by g at x, I'm saying, okay, let a1 represent the numerator and x minus r represent what? The linear factors of g. Very, very important. And to this factor, I'm assigning the sum of m partial fractions. The sum of m partial fractions to that. Okay? And I can keep on doing this until I reach the last linear factor of this m partial fraction in this x minus r to the exponent of m, being the very last factor that I will have in that order of increasing exponents. Okay, and if that is true, I have done this for each distinct linear factor of g at x. Now the second thing that I need to learn or note about this, I can do the very same thing for any other thing that can be provided. For example, I can say let x squared plus px plus q be an irreducible. Let it be an irreducible quadratic, because we can see that this is written in the format of a quadratic. So what I can do, or what I can say there, my color is not the way I would wish it to be. Let me just try to increase the brightness as I continue with this. Let me just try to increase the brightness. Okay, I will assume that things are a little bit better. So I can let x squared plus px plus q be an irreducible quadratic factor, just as I have let that x minus r also be a linear factor. So the same thing I will do for this statement, just trying to show you exactly what this really means. So we will let that x squared plus px plus q be an irreducible quadratic factor of g of x. Okay, so that x squared plus px plus q has no real roots. Okay, so if it doesn't have any real roots, it must have imaginary roots. That's one thing. If I let x squared plus px plus q be an irreducible quadratic factor of g at x, that is simply to say that x squared plus px plus q has no real roots. It has a complex roots, we can say. So we can say, suppose that x squared plus px plus q is the highest. Suppose that it is the highest power of this factor that divides g at x. Then to this factor we also assign the sum of the n partial fractions. Now, the very same thing that we have said with the very first one, we are saying with this second one. That's exactly what we are doing here. We did the very same thing to this factor. We assigned the sum of the m partial fractions, and we are therefore saying also to the second one, then to this factor, we assign the sum of the n partial fractions. So we are in essence going to do the very same thing there. Now, because we are dealing with a quadratic, in this one, we were dealing with a linear factor of g at x. This one, x squared plus px plus q, it's an irreducible quadratic factor of g at x. So that this has no real root, okay? And we said suppose that this is the highest power of this factor that divides g, okay? So then to this factor we will assign the sum of the n partial fractions. So how are we going to do that? Now here we are going to try and use different alphabets since we are dealing with a quadratic. Now what we are going to say there is that we will say, okay, b1x plus c1 divided by x squared plus px plus q to exponent 1 plus b2x plus c2 x squared plus px plus q to exponent 2 b3x plus c3 x squared plus px plus q exponent of 2. And I can keep on doing this for b and x plus cn divided by x squared plus px plus q exponent of n. This is exactly what I can keep on doing. I can keep on doing that. I can keep on doing that. And I think this becomes very clear to us because we are doing exactly the same thing as we have done in the first one. This is something that we need to take note of. Now, in the first one we said we have a linear factor x minus r to the exponent of m as the highest power of x minus r. So we are taking m and we are making m the highest power of x minus r as a factor. We know that a factor is a number that divides into something without leaving any remainder. In the context of grade 12 and mathematics, we will say that. Sometimes it can go and leave some remainders, but for this one, we will assume that the factor goes into whatever you have and leaves no remainder. Now, if exponent m was the highest exponent or it was the highest power that divides into this, remember what we said? We said, okay, on the numerator, let's assign the alphabet A1. Remember, this is integration. We want to find what A1 and A2 and A3 is. Now, because this is a linear factor where the highest exponent that we have for all x minus r is m, we said, okay, A1 divided by x minus r, exponent 1, A2, because these are different numbers. You're going to get different numbers because the exponent are different. So it will assign different numbers. Hence, we are using A1, A2, and A3. But if the exponents were the same, we weren't even going to write this because we could have just solved for 1. But because the exponents are increasing in that order of ascending, we are using different A1, A2, and A3 being the different numbers or the different whatever for this integral problem that we have, a partial integral problem. And then for that, we go to the second one. We dealt with x minus r as a linear. This time we have an irreducible quadratic factor now. Okay? We had a linear factor in the first one. In the second one, now we are dealing with a quadratic factor. And we cannot deal with a linear and a quadratic factor in the same approach. And hence we are saying, if this is an irreducible quadratic factor in such a way that it has no real roots but imaginary roots, we will suppose that this is the highest power of this factor that divides g. So what will be that highest factor? And we assigned the letter, then we do this factor, we assign the sum of the n. We assign the sum of the n fractions. Very, very important. We assign the sum of m, and I want you to be aware of something here. I did not write m plus 1, m plus 2, m plus 3. No. I said 1, 2, 3, and then you are continuing in that order where n is some integer that we cannot specify for now. The same is happening here. If we say that the sum of the n partial fractions, I'm not going to say n plus 1, n plus 2, no. You're going to say x squared plus p x plus q, because that's the irreducible quadratic factor that we have, and then we will assign 1, 2, 3, continuing in that way to the exponent of n. But because we are dealing with a quadratic, we cannot use the alphabet a1, a2, and a3. We will have to do something different from a linear, because a linear and a quadratic are different. Now we choose to say, okay, let's say for the first one, b1x plus c1 as the numerator that we have in comparison with a1. For quadratic, we will say, we are just trying to use different alphabets here. We will say b1x plus c1, and then for this one, obviously, this will be b2. You had a1, a2, you are having b1x plus c1, so meaning you will have b2x plus c2, b3x plus c3, and so on and so on. Right. I know that things are not as clear as they should even for now, but let's continue and see exactly what will emerge at the end of the day for all this, so that when we go to the different problems that we will understand exactly whether we are dealing with a linear, whether we are dealing with an irreducible quadratic factor, and what are the different methods that we can apply to that. So we are just looking at a basic, clear, descriptive way of approach when it comes to integration by partial fraction. That's all what we are doing here. Now, let me assume that we understand this from the mathematicians that wrote all this, but you know the best way of understanding whatever is to deal with the problem. So I'm not doing this as to say that yes, we 100% understand this, because I don't think there are many that does understand all this. Just a few people on the universe knows exactly what is happening, and that is out of discussion. Now, we will continue with this process with all the irreducible factors and all the powers, right? So we are saying we will continue with this process, okay, with all irreducible factors, with all irreducible factors and all powers. The base and the exponent together being a power. Okay? Now, the key thing to remember is the following. Now, the key things that we are to remember to this are, number one, is that one fraction for each power of the irreducible factor that appears, this is very, very important. We must remember one fraction for each power of the irreducible factor that appears. This is one thing that we always need to remember, and it is a key. One fraction for each power of the irreducible factor that appears. Very, very important. One fraction for each irreducible factor that appears. For every factor that appears, we must have that one irreducible factor. For every power that appears, we must have this irreducible power this irreducible factor that appears. We must assign a factor for each irreducible power. So one fraction for each power of the irreducible factor that appears. So for every factor that appears, we must assign whatever that we need to assign. In this case, we assign b1x plus c1 because it's an irreducible quadratic factor. So for each factor that appears, we must have this fraction where we assign this numerator of b1x plus c1 or this numerator of a1 for what? One fraction for each power of the irreducible factor that appears. So this is the irreducible factor that appears, but this is linear. I'm just making an example. So for each irreducible factor, for each irreducible power, for each irreducible factor that appears, we must have this one fraction for each power. So we have one fraction. So this is a power. For this power, we must have one fraction, which is a1 in this case. For this power, we have one fraction, which is a2 divided by this. And then for each, one fraction for each power. So power, we have this fraction, power, fraction, power, fraction. Power, fraction, fraction, fraction. So this is what they mean. One fraction for each power of the irreducible factor that appears. This is an irreducible factor that appears. We must have one fraction. There it is, there it is. I'm trying to explain this as much as I can. But the problems will do a lot more easier work for us. So in conclusion, we are saying for every power of the denominator that you have, you must have this fraction. Try to assign something on your numerator so that for this power, this irreducible power, you have one fraction for each. Okay, this is all what we are saying. And then secondly, the degree of the numerator should be 1 less than the degree of the denominator. Very important. The degree of numerator must be 1 less than the degree of the denominator. Very, very important. The degree of the numerator should be 1 less than the degree of the denominator. I can see that the degree of the numerator, when we look in terms of the alphabet X, I can see that the degree of the numerator is 1 less than the degree of the denominator. The highest degree of the denominator is 2 and the numerator is 1. And I want you to try and see that. So this is all just what we are saying. But it will not make sense in this way, because if we look in terms of X, this is exactly what is happening. 1, you have 2, 1, you have 2, 2, you have 1. So the degree of the numerator is 1 less than the degree of the denominator. So this is very, very true. Highly and highly true. Right. Be that as it may, assuming that we have understood that, let's go to another important factor that we need to know. We set the original fraction, the original fraction f at x divided by g at x equals to the sum. Set this equal to the sum of all these partial fractions. sum of all these partial fractions. Very, very important that we understand that. And then we will clear the resulting equation of the fractions and arrange the terms in descending powers of x, that's fine. And then lastly, we solve for the undetermined coefficients. That should be the last thing. So these are the steps required in order to solve an integral of a partial fraction. So we will solve the undetermined coefficients by either strategically plugging in the values or comparing the coefficients of powers of x. I'm not going to finish writing that up, but this is exactly the way of approach in which we must always approach integration by partial fractions. I tried my best, of course, not being 100% in explaining this, but with the problems I think we will understand much better. But this is just an overview, clear, descriptive way of approach when it comes to integration by partial fractions. And then when we are done with that, then we will begin to look at the problems. Okay, so unfortunately I will have to erase this for the first introduction. This is the first tutorial that we have on integration by partial fraction. And then in the second lecture, I believe so much that we will dive into the problems. We will try to compute a few, and then when we are done with that, we will look at simple, we will look at moderate, we will go to complicated ones and see exactly how we can build up whatever that interests us in mathematics. Now remember, the aim is to understand and try by all means to apply the best of knowledge and understanding in how we arrive at whatever that we will conclude.